In this lecture, I'm going to talk about the root finding methods. Root finding methods find where some function, f, crosses the x-axis, as in when y is equal to 0. It's very easy if you use the minus b plus or minus square root b squared for the quadratic, but after that, you have to do guesses or numerical methods. And so that's what we'll cover here. We'll cover two numerical methods. The first is bracket and bisection, and the second is NewtonRaphson. The bracket and bisection is exactly what it sounds. You try to bracket a root, and then you make the bracket smaller by bisecting, cutting it in half. So let's say you have some function, x cubed plus x squared minus 12x, and you want to find a root. So you want to find root between 2 and you say, okay, I think there's a root between 2 and 5. What's a requirement for there to be a root between 2 and 5? That means that the f of 2 and the f of 5, one has to be below 0, which is this one, and one has to be above 0. To check that's the case, that means you have a negative and positive. So the x1 is the left side, x2 is the right side. F of 2 times the f of 5 is less than 0 because minus times plus. If there's two minuses, that would mean that you're below, both are below the line. Two pluses are both above the line. You have to have one above and one below. So here we have it. F of 2 times f of 5 is less than 0. So that f of 2 cubed plus 2 squared, 2 cubed plus 2 squared, minus 12 times 2, that's minus, well, f to the power, put in 5, that's 5 cubed, 125, plus 5 squared, 2550, minus 12 times 5, which is 60, that's higher, that's plus, so you know that there's a root somewhere between them, somewhere around there. So the next thing is, you know that you've bracketed a root, so you have to bracket. To half the bracket, you find the midpoint. You bisect using the midpoint. To find the midpoint, you just add the two values together and divide by 2. And then you check the sign with respect to the midpoint. So here, we know that the root between 2 and 5, so we find the midpoint, which is 3.5. So the midpoint is somewhere in there, and we find that is the f of it above or below the line. So here we have 2.5, midpoint 3.5, and we now find the f of the midpoint. So, and when we find out that, we keep doing this until the f of the midpoint is very small, or the values start repeating. So what does that look like? In tabular form, you know your interval that you started with here is 2 to 5. You have your midpoint. You find your f of your midpoint, which is above the line, which is positive. So you replace the 5. So now instead of having an interval from 2 to 5, you have an interval from 2 to 3.5. So that's what we have here. That's f of 3.5 there, f of 2 here, and now we have our interval. And we find the midpoint again. Our midpoint here is 2.75, and we see is that above or below the line. The f of that is above or below the line. F of 2.75 is minus, so that means we get rid of the 2 and replace it with 2.75. So our interval has now halved again. Our interval started with 3, that's 2 to 5. Then it went from 2 to 3.5 with 1.5. And now this is with 0.75. Every time halving the width of the interval that contains the midpoint. Bracket and bisect. So we do it again. Our new midpoint is 3.125. It's above the line. So actually we'll bracket this way now. Let's do it in tabular form. 3.125. The f of 3.125 is 2.7. So our new interval is 2.75 to 3.125. Once again, halving the interval. We go again. The midpoint between 2.75 and 3.125 is 2.9375. The f of that is minus. So we replace, and now our interval is 2.9375 and 3.125. And you keep doing this. So here we see that. You see it's just below the line. And we're getting closer and closer. So the midpoint of 2.9375 and 3.125 is 3.03. The f of that is 0.66. So it's getting very close to 0. And you replace. I actually prefer, instead of finding the value of f, just a sign. So this is plus, minus, plus, minus, plus. We never actually used the value here. What we use this value is such that we know what to replace to make the new interval. And we keep going and going and going. And we go again, and we go again. And so every time we have our interval smaller and smaller and smaller, and we've bracketed the interval. Now, and that's it zoomed in where we started, 3 and 5, and every single jump down. So that's our first jump. Then we had our second jump with that interval, next jump here, and smaller and smaller and smaller. And those look like we're zooming in on the root that's at 3. Now, this equation, x cubed minus x squared minus 12 is has 3 roots. So you're going to have to do this method 3 times. And you have to find new brackets to bracket the other roots. The other thing is we need to know when to stop or how accurate you want. So this is independent of function. So it doesn't matter what function you have. If you say there's an interval between a and b, then what you have to say is my error, my approximate to real root, is somewhere between b minus a divided by 2n, where n is the number of times I repeat the task. So in our example there, it'd be 5 minus 2 divided by 2 to the power n. So the first time our interval is at 3, the second time is 3 divided by 2, 1.5, and so forth and so forth and so forth. So you know every time you do the algorithm, you halve the interval. And the objective is find out the appropriate n such that you're happy with how far you are away from the true root. There are, of course, issues with this kind of algorithm is if we have, for example, 3 roots in your interval. So your interval is a and b, and you have 3 roots, then one would be negative, one would be positive, but you don't know that 3 roots, you just are guessing. Or f of a and f of b is both positive or negative. It could mean there's no root or an even number of roots, for example, 2 roots here. And your algorithm can't solve that. The Bracken bisection is quite brute force-ish, and it doesn't use the information actually about the function itself. The NewtonRaphson is much more elegant and uses information about the function you have. So once again, we start with our equation, x cubed plus x squared minus 12x equals 0. And what can we do with that function? Well, we immediately can do 2 things. We know the function itself, and we know its derivative. And the derivative is the rate of change. So that can help us know which direction the function is moving. Here's our original function, and here's the derivative of the function. So what we see here is the derivative doesn't quite tell us where the roots are, but it will help us if we combine the 2 bits of information together. And how do we do that? If we choose a point here, for example, 5, so f of 5 is up here, the derivative is there telling us that actually you're going further away if we take the derivative. It tells us the slope of the direction away from it. But if we subtract that and shoot downwards, taking that slope, we now have a new estimate of a possible root. And that's what we do. So we define our function f and its derivative, as we have here. And we use the NewtonRaphson method, which is in the log table books, which says to predict a new root, xi plus 1, we use the current root xi minus the original function divided by the derivative. So if we need 1 initial guess at the beginning, so 5, and it gets us our new x1. So x1 is here. So x0 was 5, x1 is here, and then we do the same thing again. So And we repeat the steps until xi and xi plus 1 are close to each other. So let's go through the method. That's what it looks like. So in our example, we have our original function and we have its derivative, as we've seen before. We set up our NewtonRaphson formula of this form. So the next root is equal to the current root minus the function divided by its derivative with that root in. So if we take f of 5, we have here, shoot down, and then we shoot back up, shoot down, shoot back up. So once again, tabular form, our first guess, is 4. The f of that is 32. The derivative is 44. So to get the new root, it is 4 minus 32 divided by 44, which gives us 3.27. And then we do it again. So f of 3.127 is this, the derivative is 26. So our new root is 3.2, so 3.27 recurring, minus 6.49, which is our f at that value, divided by 26.67. 26.67. And that gives us 3.02, which is our new root. There. And we do it again. We put 3.02940 into our function to give us this value, 0.6. And we get it into the derivative, gives us 21. And so our new root is 3.0004. We put 3.004. Here it's very close to the real value. Into f, 0.008. 21.0 is the derivative, and gives us 3.0000008. So we input that. Now, the f of 3.008 is 1.6 10 to the minus 6. So a very small number. Our derivative is 21, but that's okay. This is very small. So we know we're very close, and therefore we have the root. And you just keep iterating through. It's very straightforward to do, and it's a very simple calculation. That's how you do root finding methods.